22nd of March 2016. SOM lecture number 10. After break starts.
Next item, shear strain. That is the definition here. Shear strain is defined as the change in initial right angle between two line elements which are parallel to defined as a change in initial right angle between two line elements which are parallel to x and y axis. In case of the normal strain, you are studying a change in dimension to original dimension, but whenever a shear force applied, there is a change in shape will occur. That's why you are going for the change in angle here, initial right angle. So to define this, to explain this definition, consider rectangular block. You can see the cross-sectional dimensions. In the top view. Now can you shift this axis the front view now? What this line is representing now? Cross section at the bottom. This is also talking about every horizontal line is about now. Cross section or otherwise top surface. But what about this line AB? Right hand side surface, this will be what the left side surface, and this will be a right side surface. What the angle between these two initially now? It will be 90 degrees. Now you have to study what initially what now? Line elements are nothing but what now? It is not actually line, that is nothing but what now? Left hand side surface, other one will go to bottom surface or cross section. The angle is going to be 90 degrees. Now you have to study what after applying a shear force, what change you are going to get this angle, you have to study it now. Now can you shift this? Now this will become as a centroid. Now this is which axis you have studied now? Polar. Front view and top view, which axis is common now? Horizontal. Now this will become as what now? That is about a vertical centroidal axis. Now that line AB is parallel to which axis now? Y-axis. And line AD is parallel to what? X-axis. That only what you mentioned now. Change in initial right angle between two line elements which are parallel to X and Y axis. Now I am applying a shear force. Nothing but a shear force, nothing but about which load it is now? PSL. If you apply load like this, it can be a normal load, axial tensile load. If you put it like, if you apply load like this, what happens now? Length will increase and cross-sectional dimensions are going to be decreases now. But here, what the effect of the shear force now? This will what now? Tries to slide this surface towards what now? Which surface now? Top surface, or otherwise cross-section at the top towards what now? Right. Now after applying the shear force, I am assuming that what now? This is going to be B is going to be slide to here. C is going to be slide down. Now what is B dash C dash now? What the B dash C dash now? New position of the surface at the top or cross section at the top. But what about the cross section in the bottom now? It's going to be a fixed one here, what now? A dash, B dash. Now what the new position here now? What the new position of this block now? This is representing what now? New position of the block. That is what now? The shape is going to be gets distorted. The shape is going to be gets distorted. This angle you are calling as what? A shear angle. The phi is known as what? A shear angle. Now what this shear angle will represent now? Notice shear angle, this will represent what now? By how much angle the surface on the left side and the right side is going to be gets distorted. By how much angle is going to be gets distorted. But what about this B dash C dash now? What is the dimension of this B dash C dash now? Same B. Means cross-sectional dimension remains same or changes now. Cross-sectional dimension is going to be what now? same. But if you apply a normal load, what happens now? The cross-sectional dimensions are going to be what now? Changes. Now this I am calling as some delta. This C dash I am calling as delta. Now what is shear strain definition? What the initial angle between line AB and AD? 90. Now what the final angle between AB and AD now? 90 minus 5. So this side is what now? Angle is decreased by what now? 5. Other side what now? Angle is increased now. How much angle is changed now? 5. So what the shear strain definition you made now? Change in initial right angle between two lines. Then how much angle is changed now? 5. That 5 itself we are calling as what now? Shear strain. So shear strain equal to gamma is equal to what now? Shear strain equal to what now? Shear angle 5. But how to get the phi value now? How to get the phi value now? We can consider the triangle AB, B dash. Tan phi is equal to what now? But for small, this can be written as what? Delta by L. Because for smaller angle tan theta equal to theta. For smaller angle tan theta equal to theta. So this itself we are calling as what? Finally what now? Shear strain equal to shear angle, which is equal to to find out the shear strain, what is required now? Shear angle is required, but to get the shear angle, what is required now? Delta is required. Now what is the delta value now? I am interested in gamma. To get a gamma, phi is required. To get a phi, what is required now? Delta. Now what is the delta value now? What is the delta value? What is the change in length? It's not the change in length. What the value? How to get the delta value? How much the delta? If I am interested in gamma, to get a gamma, phi is required, but to get a phi, delta is required. Pardon? Elastic constant. Delta is unknown. That is known only experimentally. That you have taken randomly now. That B is going to be what? Slide to exact position known or unknown now. It may be slide here or here or here, depending upon the shear force now. So that exact value of delta is going exact value of delta is known experimentally. So when the delta is unknown, which is unknown now? Phi is unknown. When phi is unknown, gamma is unknown. That only what you have said before the break now. None of the strain can be determined theoretically. None of the strain can be determined theoretically. So then how to find out now? With this given data, what you can find out? Can you find out the shear stress or not now? Is it torsional shear or direct shear now? Direct shear. The shear force. What the shear stress in this case now? P by A. Once you know the shear stress, then how to find out what the next step now? Shear strain by using shear modulus. Once you know the shear strain itself we are calling it about now shear angle. If you know the shear angle, what the delta now? L phi. Always for the first, just now before the break, what you have studied now? First stress, then strain by using the what? Elastic constant, then change in dimension we are going to find out now. So theoretically, what should be the first step you have to do it now? But most of the questions they are asking about now, find out the shear angle. So theoretically, what is the first step now? shear stress. What the next step now? Shear strain. G is equal to what? Shear modulus is equal to what now? Shear stress by shear strain. Then gamma is equal to what now? Tau by G. Now we have find out the shear strain by using shear modulus. Now the shear angle is equal to what now? Shear strain. Then delta is equal to what now? Delta is equal to what now? Pi into L. In the previous example also, first what stress, the Young's modulus calculated by what? Longitudinal strain is calculated by what? Young's modulus. Then you are going to find out the change in length. Then you are going to find out the final length. This was the procedure is going to be used theoretically now. But in this block, now what is the normal strain in this block? What is the normal strain on the cross section? What is the normal stress on this cross section? 0, because there is no change in dimension. Why? Because there is no normal load. Normal stress on the cross section will be 0 because change in length is going to be, change in dimensions are going to be 0 cross sectional dimensions because there is no normal load. But what is the normal strain in this block? What is the normal strain in this block? 0 or non-zero? Non-zero. On the cross section it is 0. But what you have said, this is nothing but a pure shear state of stress. Due to this one you are getting a one shear stress. Then complementary shear will be there now. This comes under what now? Pure shear state of stress. What is the pure shear state of stress you have studied now? Sigma x and sigma y is going to be 0. On this case you are going to get a normal or shear now? Shear. Then you are going to get a complementary shear will be there now. There is no normal stress. But this comes under what now? Pure shear state of stress. So on the cross section they are getting only shear now. But what about this diagonal now? This diagonal is elongated or contracted? Elongated. What about the other diagonal? Contracted. Why now? When there is no normal load, why you are getting the? Because of the oblique plane. This is a shear load for this cross section. But what about this plane now? AC is going to be a one diagonal, BD is going to be one diagonal, but the diagonal is an inclined load or normal load now. That only what you have said is always on oblique plane you are going to get a normal and shear will be there now. One diagonal will be increases, other diagonal is going to be decreased now. When you are studying the pure shear state of stress, what I mentioned now, always what now? Normal stress 0 or non-zero you are studying now. Sigma x and sigma y 0, but on oblique plane always what now? Normal stress is going to be there now. This diagonal, what is AC now? These are the two diagonals. But after applying the what, shear force, what about this diagonal now? One diagonal is going to be elongated. Elongated means which strain is going to be there now? Tensile strain. Another diagonal is going to be what? A contracted. One diagonal will be elongated, other diagonal is going to be contracted now. This AC diagonal is elongated or contracted. Now which strain will be there now? Tensile strain. This is what now? contracted. Now to find out this is what generally a standard engineering service question now. They are asking about to find out the what now? Strain on any one of these diagonals. Find out the normal strain on the AC diagonal. How to find out now? Using that oblique plane. What the normal strain equation was written now? Normal strain oblique plane was written as what now? 1 by 2 epsilon x plus epsilon y. 1 by 2 epsilon x minus epsilon y cos 2 theta and gamma xy by 2 sin 2 theta. So using that one, you have to find out the what now? Equation now. And this diagonal angle will be what? 45 degrees. You have to take it now. So in that oblique plane equation, you have to substitute the what now? Theta equal to 45 degrees. And epsilon x and epsilon y is going to be what now? This is going to be 0. Only which strain is going to be here now? On x and y side, which strain is there now? Shear strain. But in this figure, what now? What the neglected now? When you are going to get this deformed shape now, in this case, which one is neglected now? Bending is neglected. It is a TSL. Every TSL equal to what now? A shear force and a bending moment. What the diagrams here now? SFD is a rectangle and BM is going to be a triangle. So you are considered only which effect you are considered now? Shear force effect is considered, but bending is going to be what? Neglected. Now which one is contracted? Now what the reaction here? What the direction of this couple now? Clockwise. And the reaction will be anti-clockwise. Then which side is contracted now? Right side is contracted and this side is going to be elongated. Then you are going to get a what now? You will not get a straight line, you will not get it now. So the bending effect is not considered here now. We are neglected the what? The bending moment effect is neglected here now. So this is what? This is the shape you are going to get only considering the shear force now. Why bending moment is neglected now? Bending moment effect is neglected. Bending moment equal to what? A load into what? A length. Is a beam or a block? Block. What's the difference between a beam and a block? Beam is going to be very lengthy. Length is so many meters and cross-sectional dimensions are very small. So in the beams, which effect is more now? Bending moment effect is more. But here is what is a block. Length is going to be less. So what the bending moment is the fixed end now? P into L. So bending moment is going to be less or more now? Less. That is going to be neglected. But in the beams, which one is going to be neglected now? Then the shear force is neglected. Bending moment effect is going to be considered. Here, the deformation due to bending is going to be what? Less because bending moment is less. This one and this one both are going to be same or not? If you are going to rotate that figure by what now? 90 degrees in the what? Clockwise direction, you are going to get this only. If you rotate that figure by 90 degrees, what do you get it now? Both are going to be what? The same. What the difference here now? This will be called as a beam because length is always what? Meters. Cross-sectional dimensions are in mm. But this is what the length is going to be less. For this one, what the SFD you have studied rectangle and BM is going to be what? Triangle. Here also going to be same. But the bending moment effect is going to be what? Less now. But in this case, which one is more now? Then when the beam for the bending is going to be considered, shear deformations are neglected. Here what? Which one is neglected now? Bending moment is effect is neglected, you are considered only shear now. But in one of the gate papers, this was a question is given. A block is what? Fixed at the bottom and subjected to a tangential load at the top surface. Then the deformation of the block due to shear force, bending moment and fall load, both shear force and bending moment. both shear force and bending moment, both you have to consider. But most of the students they are going to consider only shear force because in the textbooks they are considering this only. But they will not mention what a bending moment is going to be neglected now. But in the question is asked what now? Deformation occurs due to what now? Shear force or bending moment or tensile load or what now? Shear force and bending both you have to consider. Suppose the option of shear force and bending moment is not there, then you have to go for what? Only shear force should be considered now. In the beam, the shear deformation is neglected because it is very less when compared to bending now. But in the blocks, what now? The bending moment effect is going to be neglected. Only shear force is going to be considered now. Starting with the every one now, it will be interconnected. There is no independent now. What the conclusion here now? What the conclusion from this types of strain topic now? The conclusion from this types of strain topic now? None of the strain can be determined theoretically. To determine this strain theoretically, we need the elastic constants are required. So the next we are going to discuss the elastic constants. How to find out that elongation and contraction in the diagram in what answer now? By using that oblique plane equation now. On oblique plane, what the normal stress was written now? 1/2 sigma x plus sigma y, 1/2 sigma x minus sigma y, cos 2 theta and tau xy sin 2 theta. To get a normal strain, what you have studied now? Sigma x by epsilon x, sigma y by epsilon y, and tau xy by what now? Gamma xy by 2. Elastic constant. this was the case you have studied. But your shear force applied on which face now? Top face. Now your shear force applied on the right side. Now which one is what a slide on the right side? Now your which lines are distorted now? When the load is applied on what the shear force applied on X face, this what now? Suppose you consider Y, this will be what now? Distorted now. X face is what now? Load is applied on the shear force, then Y face is going to be distorted. Now your shear force applied on which face now? Y face. Now which one is going to be distorted now? X face. So here got the shear angle of phi. Here also going to be shear angle is phi. So this case will act alone or this case will act or both combinedly now? Combinedly will be there now. Complementary shear is going to be compulsory or not now? Due to this one you are going to get tau xy. Due to this one you are going to get the tau xy. So both will act what now? Simultaneously now. Every shear stress will be associated with what now? Complementary shear now. If both are acting, what happens now? X phase distorted or Y phase distorted or both are distorted now? Both will be distorted. Then what the combined shape you are going to get it now? If both are acting simultaneously. Here what when you apply the force like this, this block what this X phase will move horizontal or vertically. This X phase will move horizontal or vertically. It will fly horizontally. Here Y phase is moving vertically. When both are acting what now? Neither this X phase move horizontally nor Y phase will move vertically. Then this is going to be what a distorted shape you are going to get it now. And what about this angle now? What the shear strain you are going to write down here now? What the change in angle now? What this angle now? What this angle now? 90 minus 25. What the gamma now? And phi is equal to what a gamma by 2. So what this value now? Gamma by 2. That's why your strain tensor what you have done it now? You have replaced the gamma by 2, you have replaced it now. Because every shear stress should associate with what now? Complementary shear. Here one reaction will be there. Now these two are causing a couple in which direction now? Clockwise. Now some of the couples are not zero. Here one force upward the reaction. These two will cause a couple in what now? Anti-clockwise. The sum of the couples should be zero mean what now? Both should be acting. When both are acting what now? When shear force acting X phase, Y phase is distorted. When shear force acting on Y phase, X phase distorted. When both are acting what now? Both the phase going to be get distorted. They are going to get what? That's why in that what a strain tensor you replace the what now? Phi by gamma by 2. Now this you have studied. What the necessity of elastic constant? They are used to what now? Are used to determine strain to determine strain theoretically. Or what you can call it are used to obtain hence the strain relationships next for a homogeneous and isotropic material is already discussed now. The number of elastic constants EC representing elastic constants are 4. E stands for Young's modulus, or what is the name now? Modulus of elasticity. Young's modulus or modulus of elasticity. G is replaced by what now? Some of the Indian answer textbook they are using the what now? C. G or C is representing what now? Shear modulus or modulus of rigidity. G stands for what? The shear modulus or modulus of rigidity. K stands for bulk modulus, and the mu in some of the Indian author textbook they are represented by 1 by m. 1 by m. E represents Young's modulus or modulus of elasticity. G represents shear modulus or modulus of rigidity. K is bulk modulus, and mu is the Poisson's ratio. But in the textbook sometimes they are also using about G. In place of G they are in the C. And mu they are represented by 1 by m. Because some of the peers, but these are the actual representation for the G only. But some of the peers use exams what now. They are using the what now. Directly the notation from the Indian author textbook, some of their what now. Then at that time what now, the G and what now. And they will also not mention now. What is it? The C is representing shear modulus. Next. For a homogeneous and isotropic material, the number of independent elastic constants, IND stands for what now? Independent elastic constants are 2. Every material tension test is conducted. From the tension test, sustain curve, your study the Young's modulus will be obtained, and the mu is obtained experimentally. If you know E and mu, what now? The remaining K and G are going to be determined relations now. So out of the 4 elastic constants, we need the 2 elastic constants. If you know E and mu, the remaining can be obtained by using your what now? Relationship between elastic constants. Subject is restricted what now? Homogeneous and isotropic. But in some of the examinations they are also asking for what now? Especially engineering service examinations. Every year what engineering service examination still know what now? At least what a 10 marks questions are going to be 10 marks total. It will be deviate from the syllabus now. deviate from the syllabus, but conventional paper they are going to stick to the syllabus now. They are always in objective examination slightly what now. As per the syllabus there is no CAD, but still sometimes they are asking what now. CAD commands also what now. They are also asking now. Though they are familiar what they are going to get an advantage, they are going to get always some. It's going to be deviation will be there from the syllabus in the engineering service examination now. Your materials of you are studying only homogeneous isotropic, but they are also asking for other materials. So try to remember this number only. Isotropic, it is going to be two. Independent. Orthotropic, it is 9. 921. For that 921, you need not go now focus on that, not try to remember only that what now, number now. But you should know the definition already you have studied about now. Isotropic, anisotropic you have studied now. But probably you have not discussed the orthotropic definition right now. On the first day all this definition was given. Orthotropic definition right now. A material is said to be orthotropic. A material is said to be orthotropic when it exhibits different elastic properties, in orthogonal directions. Orthogonal means what? Mutual perpendicular direction. How many perpendicular directions are going to be there? Upon 3. Orthogonal directions at a given point. There are changes what in 3 mutually perpendicular. So it also can be treated as what anisotropic, but anisotropic what you have studied now, where direction is going to be changes now. So it is also going to be one type of anisotropic, you can call it now. Example right down now. Examples are going to be what? Any layered material, layered material like plywood is basically what a conventional material or what artificial is going to be what now? It's going to be layer by layer we are going to get it now. One is going to be what now? Plywood, other one is going to be what? Graphite they are calling now. So these are the examples for what now? Your orthotropic material. Certain relationship between elastic constant. So this is a simple topic, but generally what now? In case paper, generally one question will get it, and engineering service examination minimum 2 questions are getting on this particular elastic constant now. And if you see all the previous papers now, only from the elastic constant you will get about now 70 or 80 objective questions are available from the previous papers now. The relationship between elastic constant. This relation, most of the questions are getting from this relationship. Why is it this relationship? Because every material you know E and mu. E is equal to 2G into 1 plus mu. G is equal to what now? E is equal to 3K. there is a, even in the previous paper also never there is a derivation of this one is asked now. But in those who are preparing anybody for civil service examination, what now? They are asking the derivation, but never in the engineering service paper, what now? There are going to be derivations are going to be there. But these are important for objective examination now. From the first one, what you will get it now? First relation is to get the shear modulus E by 2. From this relation, K is equal to what now? Always what the elastic constant values now. Constant means what they should be positive or negative now. E, K and G. They are always said to be what now? Positive means what always they are going to be greater than 0. E, K, G are always what now? But what about the Poisson's ratio? May be also equal to 0. E, K and G are always greater than 0, but mu may also equal to 0. Only for one material, Poisson's ratio 0, that is the cork example. For cork, the Poisson's ratio will be 0. This is going to be used in the what now? Bottle stopper examples. If the mu is 0, means lateral strain is 0. But what you have studied now, whenever what now? Every longular strain associated with the lateral strain. Whenever I am going to pull it, what the length will increase, cross-sectional dimensions are going to be decreased. But for me, what only length should increase, cross-sectional dimension should be 0. Then at that time, cork should be considered now. It will not exhibit any lateral strain in other directions now. That is going to be used in the what a bottle stopper example. Bottle stopper. Generally, what hospital, what a saline bottles are going to be used now. Nowadays, they are getting plastic bottles, still they are going to the glass bottles. That is going to be closed with the what now? Cork is going to be used now. So wherever the bottle stopper examples, bottle stopper, the cork is going to be used because the Poisson's ratio 0 means lateral strain 0. Even in presence of longular strain, if the lateral strain should be 0, the cork should be selected the material. If you use any other material, what now? Every longular strain will associate with what now? Two lateral strains will be there now. From this equation, K should be positive or negative or 0. From this, K should be positive now. But this value, from this equation, what now? You substitute any value of Poisson's ratio. Always what the G will be positive only. But what about the K value now? K may be positive or negative, depends upon the what of Poisson's ratio. If the Poisson's ratio are taking the 1, then this will become as what? A negative now. But K should be positive or negative now. If the K should be positive, means what? 1 minus 2 mu should be what? Greater than 0. Means mu should be less than or equal to half. So for every engineering material, the Poisson's ratio upper limit will be what? 0.5. If K should become positive, if K should be positive, 1 minus 2 mu should be for engineering materials. Will be what lies between 0 and a half. than what else? This is a negative now. All these values need not be remembered generally, they are going to be given in the generally for concrete. Civil engineers are going to deal with the concrete for the input. This is what now? 0.1 to 0.2. Metals is 1/4 to 1/3. A different type of rubber will be there. This rubber will come under what? Elastomer. Rubber, paraffin and wax. For them it will be 0.5. Whenever a Poisson's ratio 0.5 what now? The change in volume will become 0. Then at that time what now? The material behave like a perfect plastic material. When the mu got a 0.5, change in volume 0, then that material you are going to call as what now? Behave like a what now? Perfect plastic material. That's why entire your metal forming, you are dealing with the plastic or elastic now. Entire metal forming, you are dealing with the plastic. There you are going to assume the Poisson's ratio is going to be 0.5. That's why you are changing the, assuming the volume is going to be change in volume is 0. Behave like a perfect plastic material. Entire your sheet metal operation, rolling, forging, blacksmithing. What the assumption is going to be made now? Change in volume is going to be 0. Change in volume is 0 means what now? Poisson's ratio 0.5, then this will become as what now? Perfect plastic material. More or K is more or G is more now. Whether Young's modulus more or bulk modulus or shear modulus, out of these three, which one is more now? Young's modulus? Young's modulus? Bulk modulus. What is the sequence now? Depend upon mu. Metal, non-metal. Metal. Important ज़्यादा रहता है. Then bulk modulus. All metals. Next, last one is G. Non-metal. Bulk modulus. Are you seeing number is studied. We are expecting. But it also is what the correct analysis. For metals, always what Young's modulus greater than bulk modulus greater than what now? Shear modulus. Bulk modulus is infinity. Bulk modulus may be infinity also. Bulk modulus may not be negative. Even infinity is also positive value only. Incompressible. You are going to study about the fluid. Compressible fluid and incompressible fluid. Liquids are called incompressible. There is no change in volume. So the case infinity means what? That material will become as what? Incompressible. Means what? The overall volume is going to be same, but dimensions are going to be changed. Sheet metal passing rolling will what happens? Dimension will change, but overall volume is going to be what? Same. Lower and upper limit. G and K in terms of what is the limit for the mu now? 0 and 0.5 half. Now we can substitute what you are getting now. This will be what now? Now G is more or E is more. Now what is the limit for G now? Lower limit will be E by 3 and upper limit is going to be E by 2. So for any engineering material, the shear modulus value lies between what now? 1/3 of Young's modulus and half of the Young's modulus. So always what E is more or G is more? E is more. E is always less than what now? Half of the Young's modulus. But when exactly equal to half of the value now? Only for cork. Only in cork example it is equal to half of the Young's modulus. Otherwise always it will be less than the half of the Young's modulus. But what about the K? K is more or E is more? Okay, that's it. Here is what? K is more or E is more? E is more. Here K is more. Young's modulus never will be infinity enough. So means some material bulk modulus is more, some material what now? Young's modulus is more. Initially which is more now? Young's modulus more. Here what now? Bulk modulus is more. For some material E is more and some material K is more. So depends upon what of Poisson's ratio value now. But what about the shear modulus now? Always less than half of the Young's modulus except cork now. In one of the papers there is a question is given. For any engineering, any material, what Young's modulus is equal to, shear modulus equal to greater than Young's modulus, equal to half of the Young's modulus, or less than or equal to half of the Young's modulus, like this, what the answer you are taking now? less than or equal to half of the Young's modulus now. But from this one, what you can conclude it now? As the Poisson's ratio increase, what the G is decreasing or increasing? But what about the K? Increase. As the Poisson's ratio value increases, Young's modulus will decrease, but Poisson's ratio and bulk modulus will decrease and G will decrease and K will increase. And what the limits now for G? That's between E by 3 and E by 2. K for both lower limit is same. Lower limit is going to be E by 3, but upper limits are going to be different now. Now K is more or E is more means you cannot tell it. It depends upon the material now. But always what the G is going to be less than half of the Young's modulus. Now can you write down limits for metals now? If you go for metals, what should you write down now? Metals limits are what? 0.25, 1 by 4 and 1 by 3. If you put in 1 by 4, what is the value now? Which one is more for metals now? E is going to be more now. Means if mu is less than 1 by 3, mu is less than 1 by 3, E will be greater than K. If exactly 1 by 3, both are equal. If mu is what now? Greater than 1 by 3. Mu equal to 0.5. What about the K value? He will not be what the zero now. K will not be what the infinity you are going to get it now. That is the what now. That is the case you are going to get it now. Mathematical is what you are not going to get the Young's model. If Young's model is 0, what happens now? The body will become as a rigid body. No? Change in length is what a PL by AE. If Young's model is 0, what happens? No? Change in length is going to be, then it's going to be a rigid body. No? But you are dealing with what? A rigid body, what? You are for rigid body, what? But for all deformable bodies, what? It is not going to be what? There is no perfect rigid body. These relations are not valid there. No? Which one? Is equal to. Because all these relations are what now? These relations are what now? Valid only in what? Elastic region. These are not valid in your plastic region. All these definitions are valid what? Elastic constant. Elastic constant means they are all in what? Up to propose these relations are all are elastic region only. It's not the zero, my dear friend. Then how you are going to get a deformation? No? How you are getting a deformation? No? If it's up to the E, it's going to be zero, it's going to be a rigid body. No? You are getting a deformation or not? No? Don't use this equation what in the plastic region. Don't use this region in the plastic region, I am telling you. You are not getting directly, you are using the equation. No? You should know what when that equations are valid, elastic constant in what? Then how you are going to be in the plastic region? Next item. Now from this one what the conclusion? When what you are not getting, when the physical they are perfectly not, how can you apply this here now? How can you apply this equation for perfect plastic body? Then what you are telling, the same thing you are telling. If mu equal to 0.5, you are telling it a perfect plastic body, then the equations are not valid now. Somebody is going to initiate and you are all going to follow the same thing. In your elastic region, never mu will be equal to 0.5. Never in the elastic region mu will not be equal to 0.5. That mu is only 0.5 only in the plastic region, where this is not valid now. And still you are telling what the same thing you are repeating. I given the what now, that value is going to be what now? If it is a 0.5, it will become a perfect. I am not mentioned the elastic region now. And you are applying the correct same what now? You already studied the stress strain curve you have studied. And what the Young's models you have studied now? What the Young's models you have studied there now? Slope of your stress strain curve of what now? Plastic region or elastic region you have studied now? Then what about your what basics what you have studied now? So for finally what the metals you write down now? Metals can be written as what? E is greater than K is greater than G for metals now. And somebody got answer, why don't you take the equal when exactly 1/3 what you are getting now? Equal to 1/3 means in a calculator you are substituted what now? 0.3333 like that you are substituted now. But never what now the Poisson ratio will be what 0.333 like that will not be there now. It will be 0.3 or 0.33 there now. In the calculation you are substitute here now. Substitute what now? Mu is equal to what now? 0.33 in this now. Then at that time always what now? E value will be greater than K, you are going to get it now. By chance in option is going greater, but never it will be always for metals what now? E is going to be greater than K is greater than G. In a workbook there a question is given now for structural steels, which are going to be what the reverse order is given now. This has given what a decreasing order has given now. In the workbook there a question is given what now? Structural steels. Structural steel means better what now? Mine steel, low carbon steel, but commercial name is going to be what now? Structural steel, all structural application what a mine steel is going to be used now. For structural steel, what the is about a decreasing order, but increasing order what the value are going to write down now? G is what now? Less than K, and K is going to be less than what the E are going to get it now. Let's write down the definition of definitions of elastic constant. What the E definition you are going to mention it now. As per Hooke's law, under uniaxial state of stress is obtained from what model obtained from what a tension test comes under what uniaxial state of stress. Up to proportional limit PL. PL is representing what? Proportional limit. PL stands for proportional limit. Normal stress directly proportional to longular strain. The proportionality constant between these is what? It is the ratio of normal stress to longitudinal strain. Generally, everybody is going to mention about elastic limit. What the difference between elastic limit and proportional limit? Proportional limit is about the maximum stress up to which stress strain relationship is linear or law is valid. And what the elastic limit? It is the maximum stress up to which the material behaves like a perfect elastic material. But law is only valid up to a proportional limit. But in the option, if there is no proportional limit, you have to consider elastic limit. Last year, one of the same paper about a Steel Authority of India Limited is given law is valid up to. There is no proportional limit, elastic limit is given, and none of the above is given. Some students are selected and none of the above. They got about 0 marks, got it. You have to go for elastic limit, you have to select it. If the because elastic limit and proportion are very, very close, the difference between these two values are very small now. But if both are given, you have to go for a proportion. That's why some textbook they are mentioning about elastic limit they are mentioning now. What is the necessity of Young's modulus now? What is the necessity of Young's modulus now? To determine the longitudinal strain. For a given load and given area, there are two bars having got the same area and subjected to same load. Then stress induced the same, but the materials are going to be different. One the material different, Young's modulus will be different. Then at that time, longitudinal strain is inversely proportional to means higher the Young's modulus, what is that now? Longitudinal strain will be decreases. Then change in dimensions. Decreases. So you have to select a higher what now? Suppose the Young's modulus is going to be what now? 0, what happens now? Here what a change in dimensions are going to be decreased. Generally what a tension test, which dimension are calling here now? Length is going to be what a decrease now. So based upon your requirement, what a material with what now? A material with what now? Higher Young's modulus and lower means what based upon the requirement. If you need what a change in dimension should be more, you should go for what now? Lower Young's modulus. If the change in dimension should be less, should select what a material with higher Young's modulus now. Generally for mild steel. Young's modulus of mild steel. MS representing what mild steel. 200 gigapascals. Young's modulus of cast iron. Young's modulus of aluminium. Thus I am going to consider three identical bars, same length, same diameter and same load. One bar is a mild steel, one is a cast iron bar, other one is going to be a aluminum bar. All are having same length, same diameter, same load. So in these three bars, which one is same now? Stress is same. Stress does not depend upon the material now. But what about the strain now? Different now, because of Young's modulus is going to be different now. In which case you are going to get a more longular strain. Aluminum, more length will change in length in aluminum is more than what now? Change in length of cast iron bar, and cast iron bar change in length is what now? More than mild steel. So which one is giving the more change in length of cast iron or mild steel now? Cast iron. But we are going to make this statement what now? Some students and some of the examiners also got to contradict how cast iron change in length is more than mild steel. Cast iron is a brittle material, mild steel is a ductile material. Mild steel deformation should be more and cast iron deformation should be less. But you are telling what now? Cast iron deformation is more. This is the elastic region. Ductility is about the measure of permanent deformation. Total deformation of mild steel will be what now? More than the what now? Total deformation of cast iron. But you are discussing what now? Elastic region. In elastic region always what now? Elastic deformation of cast iron will be more than mild steel. In one of the gate paper there was a question is given now. 2 bars subjected what now? Same load, same area, same now. Which one is given what? A more strain means what? Some most of it directly what now? Mild steel there because mild steel is a ductile material whose change in length is more than selected now. But he has given clearly what a stress developed is what a less than the proportion limit is given. Means you have to go for only elastic now. Then at that time what which one is going to be the more change in length now? Cast iron. But all the production teachers they are going to tell what now? Mild steel deformation is more. In the strength of metal textbook they are going to mention the cast iron deformation is more. But which answer is correct? Both are going to be correct. Here you are dealing with the elastic, there they are discussing with the what now? Plastic. Total deformation given by what? Elastic plus what? Elastoplastic plus plastic deformation. Cast iron what? Even though elastic deformation more, but there is no permanent deformation. But in cast iron mild steel what now? Even though elastic deformation less, but it is more ductile material, more permanent deformation will be there now. Every statement is going to be correct under a given condition. So try to remember the statement and also remember the under which condition. Most of the students they will remember only answers now, but they will forget about the under when they are valid now. You need only answer but question and what a condition they will not remember now. What happened? Why what the power has gone? What happened? Your true quality of what? Character will come what? In the darkness. Why don't you behave now also now? What happened now? There is no medical teacher what? Nothing will do it now. No sessional, no project mark, nothing now. Here also no even what now. So much of brightness also you can what now? Exhibit your character now. In the college what now, even if you are not teaching anything what now, because what the teachers are going to be what now, some sessionals are going to be there, lab marks are going to be there, project marks are going to be there. There you have to what upright now. Then you have to create what now, only in the darkness you have to create it. But here what, medicine teachers what now, they are not going to do. Medicine is not giving a degree. Then why don't you what now, afraid of in front of the teacher? Some of the students are going to be what now? They are just like a bandar. And he is surrounded by group of bandars. If one bandar will do one activity, group of bandars will do the same. Because bandar for the God is not given anything. But God is given a human being life now. But we are forgetting about what now? Somebody got a shouted now. We are also going to be shouted now. You don't have either bandar or about the kutta. But what happened to all of others now? Sorry to use this word now. Your student class is completed. Try to what now? Probably first day made shortly 6 months to 1 year you are going to be placed in a responsible position in the society. Try to first learn the self-discipline. Subject is going to be secondary now. Subject anytime we can learn it now. But without discipline there is no use now. And somebody what should not teach what now? You should not what because the teacher what now? You should not change your what now? Behavior now. Even in the absence of the teacher also what now? Your character and your discipline is going to be what to decide your what now? You are in this level now. What you are educated or uneducated now. Simply telling what a B.Tech and M.Tech. But your character and discipline is what above than the what now? Uneducated people now. Then what the difference? They are going to be better than what now? Educated what now? Engineers now. Mechanical engineers going to some values going to the society now. Please don't try to degrade them now. So in all these three cases, which one is same now? In all these cases, what are which parameters are same now? Specific is same. Always under static loading condition. Under static loading condition, stress always independent of the material. Stress always, that's why what the stress here is now? Axial stress P by A, bending stress M by Z, torsional shear stress P by Z3. So under your static loading condition, the stress depends upon only two parameters. What are they now? Externally applied load and cross-sectional dimension. It does not depend upon the length and does not depend upon the what now? Your material now. Depend upon only two now. Axial, bending, torsional, direct shear, they are all what now? Numerator you are going to get a load and denominator you are going to get a cross-sectional dimension. The geometrical property will change. But all the geometrical area, section modulus, polar section modulus, they all depends upon what now? Only a cross-sectional dimension. Then all these three cases what the stress induced is going to be the same. But the strain is going to be depend upon what? Which one will depend upon the material? Deformation as well as strain will depend upon the material. But in case of dynamic loading case now, impact loading case, material stress also depend upon the material. But in the static externally applied loads what now? Always the stress is independent of the material now. In all this case what the stress induced is going to be same. Default I'm going to write down what is let's put a Longirus strain default. Longirus strain lengths are going to be equal. But what the assumption here made anybody know here now? When this all statements are correct now? If this stress induced should be less than what now? Proportionate of the material. Less than or equal to proportionate. Suppose this stress induced is greater than yield strength, what happens now? If this stress induced is greater than yield strength, what now? They will undergo permanent deformation. At that time, which one is going to be more deformation will be there now? Mild steel is going to be what now? Mild steel deformation more than what now? Aluminium. Aluminium is more than the what? Cast iron. Cast iron what now? There is no permanent deformation now. The total deformation will be given by what now? But these are all nothing but what? Elastic region only. Elastic deformation only. Total deformation is given by elastic ED plus elastoplastic plus based upon Young's modulus we cannot decide the what now? Ductility cannot be decided. When cast iron this will become 0. But in mild steel this is very large. But this will be less. But overall what now? Because this more permanent deformation, total deformation from mild steel more. But in the elastic region, elastic deformation of what? Mild steel is going to be less than cast iron now. So total subject we are discussing this only. And your sheet metal operations you are dealing only this only. Because there you are assuming the entire metal forming, only plastic you are discussing now. Now I am drawing the stress strain curve only in the elastic region. Shastri sir has already discussed the total stress strain curve, but I am discussing only in the elastic region. Total means what now? Elastic, elastoplastic and what a plastic also you have to consider now. But in the entire subject you are dealing only elastic. proportional limit. This is about the elastic limit. This will be about the strain elastic limit. As the load increase, what the stress increase, longitudinal strain also increase up to certain reading, what now? There is going to be linear relation will be there now. So that up to what the maximum stress, the linear relation is valid. That limit you are going to call about a proportional limit now. And what about this elastic limit? If I go above this one, what happens now? Material goes into elastoplastic region. Little bit of region will be there now. But now this total region will be called as what now? Elastic region, ER. Means as the load increase, what now? Stress increase, strain increases. But in between what? Anywhere between O and B. In between anywhere O and B. If I remove the load, what now? Curve will follow the same path and reaches the what now? Origin and the x coordinate is becoming 0. X coordinate is becoming 0 means what? The strain will become 0. So this total region, elastic region. So if anybody asks what's the difference between elastic limit and proportional limit now? Both are in elastic region only. But the proportional definition now, it is a maximum stress that, or maximum stress up to which what now? Hooke's valid, or stress strain relationship is going to be linear. And what about the elastic limit now? Because I don't know which word I have to use out. Even I mentioned what a bandar means what now. I don't know what he's about, life is what now. Was then bandar I don't know which life is going to be there. I don't know. He deserves what now? Belongs to which category I don't know. He not belongs to human being and it not belongs to animals also. And this category what now? Human being can tell it and what now? Animals can threaten or this category is what now? So the slope of this curve we are calling as what now? This will be what now? The slope of your what? The stress versus strain curve up to proportional limit is nothing but what now? Young's modulus. In last year 2015 GATE paper there a question was given. Probably work question is there. Change in stress is given, change in strain is given, and Poisson's ratio is given. Asked to find out the shear modulus now. Change in stress given, change in strain given is but what now? Young's modulus is given. Directly Young's modulus not given. A bar is subject to tensile load, then it found that change in stress is so many megapascal, change in strain is given, and probably what now? Shear modulus is given. Asked to find out the Poisson's ratio, etc. now. So with the change in stress and change in strain, what you can find out now? Young's modulus. Young's modulus is the what now? Slope of engineering stress versus engineering strain curve up to proportional limit. And if I the proportional limit definition now, then this is also be very, very small now. The curve is between these two is not a straight line, it will be what? This blue color line is what now? It is not a curve, it is a straight line, it is not a straight line, it will be what now? Deviate from the straight line. These are going to be very, very small, different values are going to be what now? Very, very close now. Once I am defining the proportionate is the maximum value of the stress up to which what a Hooke's law valid of stress strain relationship is going to be linear. Or elastic is the maximum stress up to which what a material behave like a what? Perfect elastic material. So each and every statement made in Santhamet and machine design are going to be valid in the elastic region now. Now suppose this is going to be a cast iron curve now. Now where you are going to get a mild steel curve now. Mild steel curve will come on the left side. Because of what Young's modulus more means what a slope is more. Slope is more means what a nearer to y-axis or nearer to x-axis. Y-axis. But what about the aluminum curve we are going to get it now? Right side. Because of Young's modulus less means what now? Slope is less. Slope is less means what? Y coordinate is more or x coordinate is more now. Then at that time the curve is going to be nearer to what now? X coordinate, that is x-axis now. So the three stress strain curves are given, which is the more Young's modulus means what now? The curve which is nearer to y-axis will have the what now? More slope means what? More Young's modulus. More Young's modulus means what now? It will exhibit the more resistance to deformation. Then at that time what now? Change in length is going to be less. And the curve which is nearer to x-axis will be the what now? Nearer to x-axis means what now? Less slope. Less slope means what now? More change in length you are getting, more strain you are going to get it now. Not ductile. Here ductile is not used now. Ductile what is what now? Ductile is a major what now? Plastic deformation now. Elastic region you are not in the ductile and brittle now. Based upon this Young's modulus values you cannot tell ductile and brittle now. Ductility is what a measure of what now? Permanent deformation now. But here what now? Young's modulus less means what now? You cannot tell what whether it could be ductile or brittle now. You cannot tell it here now. In the elastic region, what region there is no ductility and there is no your other one is what now? Ductility and other than malleability, the words are not going to be used. The ductility is a measure of what now? Permanent deformation now. If this is going to be a cast iron curve, this will be aluminum curve, mild steel curve. Now if I draw the what y coordinate is same, suppose what the stress is going to be same, then what about now? X coordinates are different or same now? Suppose what I written for a given stress, if the stress is going to be same, now this is intersecting at what the three different points are same points now. So then what about the X coordinates now? Different. Whose X coordinate is more now? Aluminium. Then what now? Cast iron, which is greater than the what now? Mild steel. That only what here at the higher the Young's modulus means what now? This is what a higher Young's modulus means what now? Lower strain. And aluminum is going to have the lower Young's modulus because of what now? Slope is going to be less, nearer to x-axis means it's going to give the what now? More change in length. This curve here could call it what a cast iron curve. This will be what now? But 90% of students Young's modulus means directly they are going to tell what a stress by strain. Some students are going to tell normal stress by normal strain. And some students are going to tell what now? Normal stress by longular strain. Better tell it what now? Young's modulus is defined as what now? Under uniaxial state of stress of two proportionate, it is a ratio of the what now? Normal stress to longular strain. That is the exact definition now. But 90 directly stress by strain is Young's modulus. So remaining all you have tried on the same line directly I am writing now remaining. What the G now? G is about the shear modulus or modulus of rigidity. Shear modulus or modulus of rigidity. Once again, as per Hooke's law. As per Hooke's law. Under pure shear state of stress is obtained from the torsion test. A torsion test is not conducted because of what now? If you know E and mu, directly you will get the G value. For every material only tension test is conducted, torsion test is not conducted. Torsion will come under what? A torsion test is pure torsion. Pure torsion will give what now? Pure shear state of stress. What the pure shear state of stress you have studied now? What the pure shear state of stress you have studied? Sigma x and sigma y, the biaxial or uniaxial now? Biaxial, which one is 0 now? Sigma y is 0. Why a pure shear you are mentioning? Because it is obtained from the torsion test. But torsion test is conducted what now? It comes under pure shear now. Tau xy equal to tau. But every material torsion test is not conducted because of what now? If you know E and mu, directly you get the G value now. Once again, up to proportional limit. Shear stress directly proportional to shear strain. The proportionality constant between these two is what now? So G is equal to what now? The ratio of shear stress to shear strain. So sometimes in place of shear strain, what you can call it now? They are also calling it shear angle. Shear strain equal to shear angle. But actually it should be a shear strain, but sometimes they are calling it shear angle. So with this one, what you can find out now? You know how to find out the tau. If you know the tau, then what you can find out the G by using your what now? The gamma can be determined by using your shear modulus. Next is what the bulk modulus. Once again is what now? Remember once again how we are going to get the G? Slope of your what now? G the what? The slope of E the slope of what you have studied now? Stress versus longitudinal strain curve. After conducting a torsion test, you will draw a graph is what now? Shear stress versus shear strain curve. So what you have tried on G now? Slope of your shear stress versus shear strain curve up to proportional limit now. And the slope of what? The shear stress versus shear strain curve up to proportional limit. Once again, as per Hooke's law. Under hydrostatic state of stress. Hydrostatic state of stress. Under hydrostatic state of stress. What the hydrostatic state of stress now? Is a triaxial. Under triaxial, how many stress you have studied? 6 now. So what is hydrostatic state of stress now? If sigma x, sigma y, sigma z are going to be equal and shear stress are going to be 0. Means, how to define the hydrostatic now? When a point is what now? Subjected to what now? subjected to equal normal stress in all the three perpendicular directions. Only means what? There is no shear stress now. The hydrostatic case, that is sigma x is equal to what now? Sigma y, sigma z. Tau xy equal to tau xz equal to tau yz equal to 0. When a point is subject to what? Equal and like normal stress, equal and like in three mutual perpendicular directions only, then it is going to be called as what now? Hydrostatic now. Once again, up to proposed limit, we are writing the what now? Normal stress proportional to volumetric strain. Then bulk modulus is defined as the ratio of what now? Normal stress to volumetric strain. Under hydrostatic state of stress, everybody is going to simply call the what now? It is the ratio of normal stress to volumetric strain. But under hydrostatic state of stress, you have to mention now. When this is valid, this is for solids here written, but this is in case of fluids now. Which fluids now? Compressible fluids now. That is in case of gases, what now? The bulk modulus is defined as what now? Minus PV by delta V. Why that minus sign is coming down? And the pressure is going to be increases, volume is going to be what now? Decrease. The change in volume will be negative. Now the denominator is going to be negative. As the pressure increase, what are the change in volume is going to be decreased. So this will become as negative or positive? No, negative. And this negative and negative will become as what now? Positive. K should be a positive value. But some textbook in place of minus sign they are taking a mod, they are taking now. But when you are putting the minus sign, there is no need to put the mod now, because already this will be a negative, and the negative, this change in volume is going to be negative. Then overall you are going to get a positive now. If mu is equal to 0.5, incompressible fluid, what happens? Incompressible fluid, what now? Which is zero now. Incompressible means what? There is no change in volume. Then at that time, what now? K will become as what? A 0.5. If the K equal to 0.5, it will be called as what? Incompressible. In one of the paper, what? A material neither what now? Expands in volume nor contracts in volume. Then its Poisson's ratio will be means what now? 0.5. Neither expands in volume nor contracts in volume in what now? Volume is can be what the same. There is a perfect plastic we are going to call it now. Then its Poisson's ratio will be what now? 0.5. Consider cube. Now this will come under what now? Hydrostatic state of stress. How many stress are developed on this face now? Only one. Which stress? The normal stress. What the normal stress now? P by A square. And what the normal stress in y direction also? P by A square. Load in all the directions are same, areas are same, then automatically what now? Stress in all the three perpendicular directions is going to be same. So this representation of what? It will give the what now? Hydrostatic state of stress. Sigma x is equal to sigma y is equal to sigma z is equal to what? Sigma. And the shear stress are going to be 0. Then in this case what the volume will change or distortion will occur now. Only volume is going to change, there is no distortion. The cube will remain as a cube. There will not be any distortion. Only volume is going to be increased. Only volume of cube changes. There will not be any distortion. So in this case what, how to find out the change in volume now? How many ways you can find out the change in volume now? Either using bulk modulus, change in volume can be given by what now? Either sigma V by K. What the other method anybody know? You can also use the epsilon x plus epsilon y plus epsilon z also can be used now. Which equation better now? This equation always is valid now. But this equation valid only when now? Hydrostatic now. So when a bar subjected to axial loading, you have to go for this equation only because that is going to be a uniaxial. Only under hydrostatic state of stress only you have to use this equation. But this equation, there is no constraint for this equation. This equation can be used any case now. Epsilon x plus epsilon y plus epsilon z. That is for uniaxial or biaxial or triaxial now. All the cases can be valid now. There is no constraint for this equation, but this is valid under only hydrostatic now. Here why there is no distortion here now? No shear stress. Where? Then there is no shear. But here shear stress not only 0 on this one. Even in what oblique plane is also going to be 0. is a peculiar case. Here every plane is a principal plane. Generally principal plane how many are studied? No, 3. Only on 3 planes shear stress will become 0. But here is what now? Under hydrostatic condition, on every plane shear stress will become 0. Once every plane shear stress will become 0, what now? Every plane is a principal plane. Since there is no shear stress, there will not be any distortion now. Suppose this will be a compressive load now. This is a compressive load. At that time what now? Distortion will be there or not? Cube will not remain as a cube now. This will be about now? Sigma, but this will be minus sigma now. At that time what is not a hydrostatic? At that time what now? Not only volume, distortion also going to be occur now. Only under hydrostatic condition. Suppose it is like this. Here also put on this 3 plane there is no shear now. Here also on this 3 plane there is no shear. But here what? A volume change or what now? The cube will remain as a cube or what now? Here what? A distortion also going to be there now. Why now? But here there is no shear stress. But why you are getting distortion? Every plane is not a principal plane. Here only these 3 planes are a principal plane. But on that condition what now? Every plane is a principal plane, means all the infinite planes are principal plane. So their principal plane lies in which direction now? All the directions. That is going to be what now? Peculiar case now. Here, every plane is a principal plane. Every plane is a principal plane. Principal plane. Hence, there will not be any distortion. But here, how many principal planes are going to be there now? 3. So, remaining planes, what the shear will be there or not now? So because that shear stress what happens now? Distortion also going to be there now. But somebody how to get it? What every plane is a principal plane. You know the shear stress equation now. First you assume this quantity belongs to x and y. Now can you write down the shear stress? What the shear stress equation now? Oblique plane, what the shear stress equation was written now? Minus 1/2 sigma x minus sigma y sin 2 theta and tau x y cos 2 theta. Substitute now. Sigma x equal to sigma, sigma y equal to 0. What does tau x here going to get it now? 0. Means you put it what now? What the tau x equation in written now? Minus 1/2 sin 2 theta but this equation valid for 2D or 3D now? 2D. Assume what this quantity belongs to these two phases now. Then at that time we can use this equation. Okay, let's substitute it now. What the sigma x and sigma y equal or not now? What this value now? 0. Tau x by 0. What about this value now? 0. But whether theta value is given or not given now? Theta value is not given, but I am getting expression what now? Depend upon theta, independent of 0. And what about the normal stress equation? What the normal stress equation? Check it now. 1/2 sigma x plus sigma y plus 1/2 sigma x, second term once again 0, third term 0. What you are going to get now? Sigma n equal to sigma. Means even if the theta is not given, I am getting what now? Sigma I am getting. Means sigma is what? A sigma is depend upon theta or independent of theta? Independent of theta means what now? On all the planes, what the normal stress now? Sigma. So here what the shear stress equation now? 0. Means on every plane shear stress 0. What about the normal stress equation now? 1/2 sigma x plus sigma y 1/2 cos 2 theta tau x y. What the value are going to get now? Sigma. But the theta value is given or not given now? But I am getting an expression in terms of theta independent of theta. Mean what the meaning of that? On every plane what the normal stress sigma. On every plane what the shear stress 0. Therefore every plane is going to be a principal plane. So this much of stress is getting only on this free plane or every plane? Every plane. That's why what now? There will not be any distortion. But if we can use these two, what happens now? In this case, what happens? Suppose if we take these two now, sigma is equal to sigma and sigma, this is what now? Minus sigma. Then this will become as what now? This will become 0 or non-zero now? Non-zero means shear stress is going to be exist now. Simply can what now? Remember what under hydrostatic condition, every plane is a principal plane, mean all the planes shear stress 0. In that case, only volume will changes, there will not be any distortion. Then principal plane lies in which direction means what? All the direction. But generally how many principal plane means what? Only 3 planes. Except in which case now? Hydrostatic condition. So here only what? Your bulk modulus concept is valid now. Everywhere what? Bulk modulus concept is not valid now. The Poisson's ratio. Once again, your lateral strain is proportional to longular strain. The proportionality constant is going to be what now? Poisson's ratio. What the mu now? Lateral strain by to take the y direction the lateral strain, x direction longitudinal. Why this minus sign is coming once again now? Poisson's ratio should be positive or negative now? Positive. What this ratio you are going to get a negative now? When a bar is subjected to tensile load, what now? Change in length is going to be decreased, change in length increase, change in diameter is going to be decreased. So this will be negative and this will be positive. What the overall ratio now? Negative and negative will become about a positive now. And once again, for some textbook there is about a mod. When you are reading the mod, once again there is no, you need not go for the minus sign now. But in tension test, for tension test, what the Poisson's ratio can write down for tension test. For the lateral strain now. Under tension test, the generally standard your engineering service question. They are giving the change in diameter, change in length, and ask to find out the Poisson's ratio. But Now to find out the lateral strain, how many elastic constants are required now? To find out the lateral strain, how many elastic constants are required now? 2 elastic constants. This will be obtained by what now? Young's modulus. But most of them are going for directly Poisson's ratio now. To determine the lateral strain, 2 elastic constants are required. This will be determined by what now? Young's modulus. And additionally, what is required now? Poisson's ratio. To determine lateral strain, 2 elastic constant, what is E and mu. In tension test, can you get a Poisson's ratio now? From tension test readings, can you determine the Poisson's ratio? From tension test readings, can you determine the Poisson's ratio? Tension test, you are measuring only change in length. There is no change in diameter. There is no provision for change in diameter. You can only measure what now? That extensometer will measure only change in length. Then how to get a Poisson's ratio now? Tension test will give longitudinal strain or lateral strain or both now. Only longitudinal, lateral strain is unknown. Then change in diameter is unknown. Then you cannot determine the Poisson's ratio. Then for every material, which one is known? Young's modulus known, means which one is known now? Lateral longitudinal strain is known. Then how you got the Poisson's ratio value now? How you got the Poisson's ratio value for every material? For every, if you want to get the Poisson's ratio, what is required now? Longitudinal strain, lateral strain. This is not tension test. But how do you know this lateral strain now? By using the strain gauges. By using the strain gauges, what a scientist got a Poisson, what now? He has got a measure the what the lateral strain. Then already longitudinal strain is there, like that what now? For every material, what now? Poisson's ratio is determined. For every material, longitudinal strain known or unknown. For every material, already tension test is conducted. Once the tension test is conducted, means what now? Young's modulus known. Once the Young's modulus known, which strain can be determined it now? Longitudinal strain already known. Then to get a Poisson's ratio, what is required now? Lateral strain. That lateral strain he has measured what now? Experimentally by using the strain gauges. Since you already know Young's modulus by using lateral strain by using longitudinal strain by using here what now? Young's modulus. And lateral strain he has measured what by using the strain gauges. Then he has like that what for every material what now? Poisson's ratio values are determined. Now by using that Poisson's ratio, now you are going to find out the what now? Change in diameter you are going to find out now. In tension test there is no provision for the change in diameter. You are able to measure only change in length now. Always what make a habit of what now? Whenever you are writing the lateral strain, you have to put the minus sign. Most of the students they will not put it now. Then automatically your Poisson's ratio value you are going to get a negative, you will get it now. Whenever you are writing the lateral strain, you write down the what a minus of what a mu longitudinal strain. Expression for volumetric strain under expression for volumetric strain under axial loading. So in this case, how to find out the change in volume now? One way is the change in volume is written. One is bulk modulus, other one is what now? Epsilon x plus epsilon v plus epsilon z. Which equation I use it here now? Is it a hydrostatic or non-hydrostatic? Is it a when the bulk modulus can be used now? Only hydrostatic, but is it hydrostatic or non-hydrostatic? Cannot be decided now. May also become a hydrostatic. They are all good now. Like nature or unlike nature now? Like nature. But without then the px, py, pz, l, b and t cannot be decided now. For hydrostatic means what? Sigma x, sigma y, sigma z should be equal and like. Already they are like in nature. But they are equal or unequal. What is required now? You should know the load as well as what the dimensions are required. So without knowing the dimension and without knowing the load, it cannot be decided hydrostatic or non-hydrostatic. So for derive the expression, which one I have to consider now? Bulk modulus I have to consider what now? Epsilon x plus epsilon y plus epsilon z should be used now. You have to do the epsilon x plus epsilon y plus epsilon z because that is a generalized equation. It may become a hydrostatic or may not be hydrostatic, cannot be decided. Therefore, you cannot go for directly bulk modulus now. What's the sigma x now? What's the sigma y? These are all equal, you are going to call it a hydrostatic, but these values are known only when you know the load and what now dimensions now. How to find the volumetric strain now? What should I call the epsilon x, epsilon y, epsilon z? Total strain. You cannot call the longitudinal strain. In this case, now with this given data, stress is known or strain is known. So when can I use that equation 1 now? Directly experimental data is given now. Strain gauge readings are given. Strain in x direction, strain in y and strain in z direction is given. Directly we can use that now. But theoretically always stress is known, strain is going to be unknown. Now what you have to do it? Now you have to write down the sigma epsilon x, epsilon y, epsilon z in terms of the known data. Theoretically which is the known data now? Always loads are given, dimension, this is known. Now you have to write down the expression for what now? Epsilon x, epsilon y, epsilon z in terms of the stresses now. You write down the expression for the water strain in terms of the stresses now. Now what the one student is going to write down like this, epsilon x is equal to, you will write down like this. These are the answers given by one of the students now. If you make the second equation. And another student will write down like this. One student is going to write down like this, other student will write down like this. Whose expressions are correct now? Both are incorrect. Both are wrong. one is the answers are correct or second one is incorrect?
Both are correct.
First one is correct.
Both are correct.
This is correct in case of uniaxial case. Is a longitudinal, lateral. This is valid for when Py and Pz are going to be 0. When Py and Pz are 0 means it is going to be a uniaxial. But when this is valid, the triaxial case is valid now. But when this is valid now, when the second student answers are correct now. Second student answer, first student answers are correct what now? When Py and Pz are going to be 0, that's a uniaxial case. But when the second student answers are correct now, when mu is equal to 0, that's correct now. This is nothing but a longinus strain. Young's modulus always gives the longinus strain or lateral strain. This means this is nothing but about a longinus strain in which direction? X. So which one is missing there now? Lateral strain is missing. When the lateral strain will be 0, and the Poisson's ratio equal to 0, means this is correct when now? If this block is made up with a cork example now. If the material of this block is going to be a cork, then at that time what now? Mu is going to be what now? 0, then at that time lateral strains are going to be 0 now. These are correct what when Py and Pz are going to be 0. So this uniaxial case is valid now. This is valid for triaxial only. All are non-zero. But what the other condition now? Poisson's ratio should be. That is about a cork as about a material. This is because the longinus strain. Is a longinus strain. The longinus strain due to Px, longinus strain due to Py, longinus strain due to Pz. But you have derived the expression for generalized case. Every time mu may not be 0. Only for cork it is 0, but you have to make the what now? Derive for generalized expression now. Then at that time this is not going to be correct now. Then what you have to do it now? Now which elastic constant I have to use it now? For this case, to find out the change in volume or volumetric strain, which elastic constant I have to use it now? None of the elastic constant is valid now. Is it uniaxial or biaxial or triaxial? Triaxial. But triaxial what now? How many elastic constant you have studied? One. Bulk modulus now. But that is valid in case of hydrostatic. What is the non-hydrostatic? But Young's modulus valid under what now? Uniaxial. But is it uniaxial or non-uniaxial now? Then what you have to do is use the superposition principle. When you are studying the eccentric axial load, what you have studied now? First you have done the axial load acting alone, then bediment acting alone. Since both are the normal stress, you are directly added now. This Px, Py, Pz will give the same strain or different strain. Px, Py, Pz will give the normal strain or shear strain or what? Normal strain. Then what do you do it now? First you assume Py and Pz are 0. It will become as what now? Uniaxial. Then you can use here Young's modulus and Poisson's ratio can be used now. Next you assume only Py is acting. Once again uniaxial. Next assume only Pz acting alone. Then you superimpose all these results now. Now first I am assuming the Px acting alone. Load Px applied on which phase now? Load Px applied on which phase now? X phase, nothing but a cross section. What this figure is representing now? Front view. So this is nothing but a cross section. This is going to be a top surface, bottom, front. So where the load is applied now? On cross section, that is on X phase. First assume only Px acting alone. When Px acting alone, now the uniaxial or biaxial now? Uniaxial. So what is the longular strain? In which direction you will get it now? X direction. How to get a longular strain? Stress in the direction divided by Young's model. What is stress in this direction now? Sigma x divided by Young's model. This will give a what now? Longular or lateral now? Longular. Then what about the lateral now? Just now you write a lateral strain equal to what? Minus of mu into longular strain. Minus of mu into. So when this row is valid now, when Px acting alone, next you assume the what? Py is acting alone. What the load is acting in which direction now? Y direction. What the longular strain you studied? Strain in the direction of the load. What the stress in this direction of load? Sigma y divided by Young's modulus. In which direction you will get it now? Y. Now this is a longitudinal. And which direction you will get it? Lateral. X and Z. What the lateral strain now? Lateral strain is always for the minus of mu into longular strain. Next, PZ. PZ is applied on which face now? Front face. Whether you can show with a dot or otherwise what inclined line, of course you can show it now. This load is applied on the back side face, and this is applied on the front side. Back side is going to be applied now. Now which one is the longular strain once again now? Z direction. This will be what now? Sigma Z by E. This is a longular strain. These are what? A lateral strain in X and Y. This is what now? Longitudinal. Longular strain in X direction due to Px, longular strain in Y direction due to Py, is a longular strain in Z direction due to Pz. Remaining all are what now? They all become as what? A lateral strain. Therefore, when this each row is valid now, when all these rows are valid now, Px, Py, Pz are acting alone. But actually what they are all acting what? Simultaneously or independently now? Simultaneously. Now when all are acting simultaneously, then you can superimpose now. How many strains are going to be there now? One longitudinal and two lateral. Both are normal strains only. Direct we can add it now. So in each direction what you are getting, the one longitudinal and two lateral, that only are written now, starting now. How it is saying? Depend upon sigma z, sigma by sigma z are what? That is a lateral strain, but they will not be equal now. That depend upon what now? Sigma y and sigma z now. Now to get the total strain now. Total strain, add all this thing now. So if I add all this thing directly, I am writing this side now. Epsilon x, otherwise what now? Total strain in x direction. Default, if you are not indicating, that's what about a total strain. So what you are getting? 1 by E sigma x minus similarly what epsilon y. First write in the stress in the direction sigma y. The remaining is in the bracket now. What the advantage of these three equations now? They are used to determine the what now? Total strain in XYZ direction, uniaxial, biaxial, triaxial now. All the cases. You are derived for triaxial means it can also be for what now? For biaxial, which one you have to make it 0 now? Sigma z. Uniaxial, you have to make the sigma y and sigma z should be 0. And what the other advantage now? Why you are finding out epsilon x, epsilon y, epsilon z? They are used to determine the what now? Change in dimensions. So this will be what now? X direction, which dimension is there now? L. Length is there now. Y direction, which dimension is there now? Thickness. These equations I am calling as what are some equations? 3. So that will quick. Above set of equations. Above set of equations. Above set of equations are used to. Above set of equations are used to determine total strain in three mutual perpendicular directions passing through a point and change in dimensions of the member under any state of stress condition. What is the meaning of any state of stress condition? Maybe uniaxial, biaxial, triaxial, or even hydrostatic also. Under any state of stress condition. For uniaxial, which one you have to make it 0? Now sigma y and sigma z. biaxial sigma z. Hydrostatic, what do you have to make it now? Sigma x, sigma y, sigma z should be equal now. But finally you are interested in the volumetric strain. How to get the volumetric strain now? Add all this thing now. At the next by substituting equation 3 in equation 2. By substituting equation 3 in equation 2. Directly I'm writing now. That is what you have to add all this thing now. Add all this thing, you will get an equation like this. Both the equation will be the same strain or not? Same strain. But shall I go for equation 3 or equation 2 or equation 4? As per the given data. So directly what now? Strain tensor is given in the question now. Strain tensor is given means directly epsilon x, epsilon y, epsilon z. Suppose stress tensor is given, you are going for this now. So as per the given data, you have to select it. But in this case, what now? Which one is known? Stress is known or strain is known now? Stress. Then you can use this equation. Suppose there is a block whose temperature increased by. There is a block whose temperature increased by delta T degree centigrade. When temperature increase, what happens? The volume will increase or decrease now? Increase. Then how to find out the change in volume? Equation 2 or equation 4 now? Equation 2. Equation 4 cannot be used by now. There is no stress. There is no load is there now. But still we are getting what now? Change in volume because of change in temperature now. Some students are going to use this. In that case, what a strain is there or stress is there? So I am going to kept a block on this flat surface now. So I am going to heat this now. Temperature increase by T degree centigrade. Dimension will change or not? Length will increase, height will increase, width will increase. So volume will change as now. Strain is there. But in this one there is no stress because there is no externally applied load. Always clearly mentioned what the stress should be there means what now? There should be a load should be there. So in this case only you have to the equation 4. In your thermal stress you are going to discuss this example. In the chapter I am going to use this equation now. Some students are telling what I am using equation 4. I am not getting the answer now. When there is no load, how we are going to get a stress? We cannot use this now. Only equation 4 should be used. Equation 2 should be used to determine because there is no stress. Sigma x, sigma y, sigma z are going to be 0. Sigma x, sigma y, sigma z are going to be 0. Now from this equation you can make the two important conclusions now. If the change in volume should become 0, what are the conditions now? Poisson's ratio should be 0.5. Means if the Poisson's ratio of a material is 0.5, whatever may be the state of stress, without knowing sigma x, sigma y, sigma z, whether it may be uniaxial or biaxial or hydrostatic or non-hydrostatic, if mu equal to 0.5, what happens now? Change in volume is going to be 0 now. But mu equal to 0.5, only 3 material, perfectly plastic material you have studied now. But for metals, less than 0.5. Now what the other condition for change in volume should be 0 now? Some of these three should become 0. Sum of sigma x plus sigma y plus sigma z should be 0. But when sum of sigma x plus sigma y plus sigma z will become 0, there should be like nature or unlike nature? No? Like nature. Suppose this block, if directly Poisson's ratio is given, Px, Py, Pz, L, Pt are not given now. But what is the change in volume now? Px is not given, Py is not given, Pz, L, Pt all are unknown now. But only Poisson's ratio is given as 0.5. Direct we can tell change in volume is going to be 0. Poisson's ratio is given as 0.3. Once again Px, Py, Pz are unknown. How it is 0? Poisson's ratio is 0.3. Now these are all like nature or unlike nature now? Then there is no possibility of sigma x plus sigma y plus sigma z is going to be 0 now. Suppose this is given as a compressive. So one value is given as a compressive load and Poisson's ratio is given 0.3. At that time, change in volume may be 0 or may not be 0. So in which case you need the what now? All these values are required now. When they are unlike in nature and Poisson's ratio is going to be less than 0.5. Change in volume will be 0 if Poisson's ratio equal to 0.5 or what now? Change in volume will be 0. Either Poisson's ratio should be 0.5 or sigma x plus sigma y plus sigma z should be 0. Another statement now. If the Poisson's ratio of a material, if the Poisson's ratio of a material is equal to, if the Poisson's ratio of a material is equal to 0.5, then change in volume is equal to 0. Then change in volume is equal to 0 under any state of stress condition. Change in volume is equal to 0 under any state of stress condition. If Poisson's ratio less than 0.5, then change in volume is equal to 0. Then change in volume is equal to 0 if change in volume is equal to 0 if some of the normal stresses in three mutual perpendicular direction, some of the normal stresses in three mutual perpendicular direction should be 0. Should be 0 means they should be like or unlike now. At least one should be unlike. Within bracket, that is sigma x plus sigma y plus sigma z should be 0. Sigma x plus sigma y plus sigma z should be 0. Out of this question, this will complete it. Number 2 questions. Chapter number 1. Question number 5. Question number 5 and question number 21. 21, 27, 29, 31, 32, 33 and 35. Chapter number 2. question number 14, that is question number 14, question number 15 and 17, 1-7. And chapter number 3, one question I forgot, question number 5 also. Chapter number 3, question number 5. So these questions try to complete directly what is based upon the class course you can do it. So tomorrow first I am going to some more problems, then I am going for the what now? Bars in a composite bar, compound bar, that is what now? Bars in series in the parallel. And tomorrow there will not be morning break, directly 7:30 to 12:30 class will be there without any break now. 5 hours class will be there, and 12:30 I am going to stop the class now.